So now we've made it to chapter 14, our last section to cover, our chapters 14, 1 through 5. We're going to be focusing on applications of the integral. So in a sense, no new content. We are going to be building on everything we've learned from chapter 13 about taking the integral and those techniques. And where we're going to start today is with a technique to integrate something that sort of comes from a product rule, integration product rule. So remember, in the product rule, we had a times b, and then we did derivative of a times b plus derivative of b times a. So we broke it up into a little separate sort of matrix. Well, we're going to take it a step further this time, and to show you this, since conceptually there's nothing new, where you understand what an integral is. It's the area under the curve. You understand how to take the three types of integrals. With a polynomial, we add 1 to the exponent and divide by that new exponent. E to the x is its own integral, and when you integrate 1 over x, you get natural log of x. The only thing we haven't done yet is how do you integrate the natural log of x? So let's start there. That's what we need integration by parts for. So I'll show you this part here. It's kind of down here. So what the formula for the integration by parts. Now, those of you who want to know and understand where this formula comes from, how it was derived, you're in the wrong major. You should be math majors. The PowerPoint, and the reason I'm diverting from the PowerPoint is it's spent a lot of time going over kind of trying to explain why this works. But what I want to do is I want to just show the method of how it, show it working. So what we're going to do is on every integral, we're going to break it down into two parts, a u part and a dv part. And we're going to go through several of them so you can kind of get experience with it. And then you do this little thing here, and I'll just show you. I've got a table set up. You'll figure out the parts, and hopefully with this scaffolding, by the time we're done, you won't need the scaffolding anymore. Just, you're able to get it all done. Okay, so let's first see integration by parts. So the first part of integration by parts is to break it down into parts. So when we have natural log of x, now again, we know the derivative of natural log of x is 1 over x. And when we integrate 1 over x, we get natural log of x. But we have never done what happens when you integrate natural log of x. And the reason is it can't be done directly. It needs to be done with integration by parts. So now we can do it. So this is going to be our u, and this is going to be our dv part. So notice we've got a dv part. Sometimes this dv part is more than just the dx, but in this case it's not. So we'll see several examples here. And I wish there was a quicker way to switch back and forth between pins, but so I've defined what u is, that's this part, and the dv part goes here. Now with the parts, what we're going to do is and again, why do we do this? Because it works. Okay, and you're going to see in the end we'll put it together. One of the parts we're going to take its derivative, the other part we're going to integrate, and that gets us back together. Okay, so the first thing is the u is just the u, so this just gets copied down here, natural log of x. And again, technically you should always have a parentheses around it because it is a function. Natural log is a function, but we get sloppy, and sometimes in the book they don't even do that. So see, the u, what you're going to do is you're going to come down here, we're going to take its derivative. So what's the derivative of natural log of x? Natural log of x, we did that up here, is 1 over x dx, because we took a derivative, right? And we're going to need that because you're going to see it's going to go over here. Okay, see the du becomes over here. So this is where the pieces are going to come together. dv, so this is dx, so we're supposed to get from dv to v. How do we do that? We integrate. So this step is the integrating step. I should switch colors. Shouldn't mix your colors, right? So we're going to integrate. So integrating dx, I guess I could put it here. So it's like 1 dx. When you integrate, think of 1 as think of it as x to the 0 power. So add 1 to that. That's going to be x to the 1 power divided by 1. So it's just x. That's all there is to it. When the integral of dx integrates to x. And what we do, that's now v, we copy it down here. So there's our pieces. Integrate one piece, copy down, differentiate one piece, and now over here we put them together. We take u times v. Now I'm going to move the x in front. I'm actually going to do v times u because it looks weird if you do natural log of x. So we're going to, and I'll change to black ink. So we've got x times natural log of x, because everything's together. Okay, so I switched orders, which is a little confusing. This is really, when I'll put it here, I really did v times u because I can. Okay, even though formula says uv, this is the same thing. Okay, over here we're going to put v, the integral of v du. So v is x, du is 1 over x dx. Now notice x divided by x, that's 1. So this is just going to become the integral of dx. Okay, so and then down here we basically just put these two parts together, right? This is the front, this is the back of the train. So our answer is going to be x natural log of x minus the integral of dx, because of that canceling. Now you might think we're done, but we're not. We still have a part to integrate, and that's what integration by parts is. It's usually several steps. Sometimes, I don't think any of our problems will have it, we'll see, but this has to be done by integration by parts a second time, and then maybe sometimes a third time and a fourth time. So it could be that you might need to keep doing this. In our case, this, remember, just integrates into x. So what we end up with is x natural log of x minus x. And again, plus a constant because we're back to an indefinite integral. But that's the answer. That's it. And so you're asking how would I have known that natural log of x integrates directly to this? There's no way. You would probably have known that. There's no way I knew that. I'm still not even sure of it, so let's give it a check. I want to show you that this does work. So we're going to then take its derivative. So this is our scratch work. We'll do that in a new color, blue. Let's go with a little bit lighter blue, just for a happier day. Okay, so we're going to take our answer, which is, this is our answer. This is what you would enter into WebAssign, or if this was a problem given to you, which it may very well be. But what I'm going to ask you to do, I've got this stored in Canvas, is I'd like you to go back in the blank one and go through the steps yourself. Put the pieces together. This is a learning style called underwriting. It's thousands of years old. Underwriting is the master teacher. I'm not saying I'm the master teacher, but the teacher, let's just call it the teacher, would write something and the student would write underneath. That's how I learned a lot of our languages, how to write. You know, you have those little books with the little dotted stuff in there. That's how I learned to write Thai as well. I got children's books and learned the Thai language, the Thai alphabet, I'm not perfect at it, but underwriting is a great way to learn because it provides this scaffolding, this support to get you to understand. Okay, remember you can always fast forward through my talks, but hopefully you find them interesting. So here's x, natural log of x. I'm just copying it down, minus x. I'm not going to worry about the c because when we take its derivative, it's going to be 0. Okay, I could put it up there, but I don't want to. I don't want to. Okay, so I do this, and I'm just going to use this notation. I'm going to take its derivative. Remember, this is our little derivative thing. You could use d dx if you want, but okay, I'm going to do the easy part first because this is a single term by itself. So the derivative of x, negative x, is going to be -1, right? This one, when we take its derivative, since it's got two pieces multiplied, it's going to be the product rule. So we take the derivative of the first part, which is, so again, if you want to separate it into a times b, maybe I should do this, where a is x, b is natural log of x. We take the derivative of a, that's going to be 1. We take the derivative of b, and that's going to be 1 over x. Okay, and then when we're done, we reassemble it as the derivative of a times b plus the derivative of b times a. And again, these orders, you could have done a times b. Don't get hung up on that. I just I like ABBA. That's a great band when I was in high school. So yeah, we're all old now, but anyway, I don't know if they're still around or not. Anyway, derivative of a is 1, so I get 1. B is ln of x. And then I do a plus, right? And then I do derivative of b, which is 1 over x, times a, which is x. Okay. 1 times ln of x is just ln of x. This is 1 over x times x. The x is canceled, so this just becomes plus 1, minus 1. Notice this part 0. Our final answer is natural log of x, which is exactly what we started with. It works. So I always say, you got a good mechanic that can fix your car. Don't ask him how, just let him do it. If you know a process that gets your car running, I in high school, I always had old cars that were 20 years old and barely could keep them running. I knew if I jiggled this or jiggled that, it would work. I didn't ask why it worked. I just knew it would work, and I didn't get stuck somewhere. Maybe I should have took it in, but college kid, not much money. That's how I got through. Okay, this is it. This is the lesson. We're going to do this several times with several different types of problems to kind of identify what's the u part, what's the dx part, and this is the whole lesson. Okay, so let's keep going. Here's another similar one, but it's got an x squared in front, not just the natural log of x. So how do we do this one? That calls for a little support there with some coffee. Okay, we're going to go identify our parts. And I believe I'm going to get this right. What we want is the part we're going to take the derivative of. We want that derivative to sort of disappear. Because you know there was some, like if negative exponents, as you started taking the derivative, the exponent just became more and more negative. It never went away. But if you had positive exponents and you took the derivative, it would go away. But in this case, x squared, if it would take two derivatives for it to go away, and then we would be integrating natural log of x, because this is sort of our natural two pieces here. It's either x squared and natural log of x. But we know that natural log of x from our last exercise, if we take its derivative, natural log is gone, right? It's 1 over x. So whenever you see natural log of x, the best shot is to put that as your u in the part that's going to get derivativized. I don't know if that's a word. Take the derivative. So what's left? This dx. Okay, so that's what we're going to call as dv. So x squared dx. Okay, and I'll start here since I'm already in red. We want to turn this in from dv to v. So what that means is we're going to integrate this part. Now remember, to integrate x, we add 1 to the exponent. Sorry. Add 1 to the exponent, so it becomes 3, and then divide by that new exponent. This is our v. We copy it down here, x to the third over 3. Okay, that's good. Our u part, we just copy it down. I like this part. This is like my favorite stuff when I get these. And then I'm going to take the arrow and it says, oh, take its derivative. So what's the derivative of natural log of x? It's 1 over x dx. Boom. Now we just put our pieces together and see what we end up with. And it's just kind of cool. So let's go back to our standard power marker. So again, I'm going to swap these because I just like, it's easier to write natural log of x and not get confused on what's in here if I put the other part in front. So this is x to the third 3. Notice u times v, u times v. So this is u times v. Okay. Down here, we're going to get v times du. V times, this part is v. X to the third over 3 times the du part, which is 1 over x dx. And now we rewrite it out. We won't quite be done because we still have a part that we're going to need to integrate, but if we're lucky, it's an easy integration. So what we get is we get x to the third over 3 natural log of x minus, right? The minus comes from the formula. The integral, now I'm going to simplify this a little. This is x to the third and x down here, so the x cancels, so this is going to become x squared over 3 dx. Now notice again, this last part is a straightforward integration. It's just a polynomial. We add 1 to the exponent and divide by that new exponent. So the front part is done. I will have to check that I'm recording. I made a bunch of videos yesterday, and half the time I wasn't recording, so I made twice as many as I needed to, but hey. Yeah, we got this minus here. Minus comes from here. Add 1 to the exponent, x to the third. It's already over 3, but we're going to divide by 3 again, so 3 times 3 is 9. See how we did that one? And then we just add a constant because it's an indefinite integral. I like that blue, so we'll bring that blue back and highlight that that's the final answer. So notice, just choose your pieces, and if we've got a natural log, that's going to be the piece we get. That's what's going to be u. Everything else becomes dv. Take the derivative of one side, integrate the other, boom, boom, there it is. Put it in its pieces. Okay, all following this formula. Well, since we could handle natural logs just fine, let's take a look at what would happen if we've got an exponential. Here's another example. This is not quite, because this is not an x squared. We can't just do this with u substitution. So what we're going to do is we're going to do it with integration by parts. And now e is one of these tricky ones. If you take its derivative, it's its own derivative. It's not going to go away. If you integrate it, it's also its own sort of its own integration so it doesn't get any worse. That's kind of what you want to do. 3 to the x is going to kind of go away. The x will go away as we take its derivative. So what we want to do is make the part that's going to go away by the derivative right here. That's what we want to make u, 3x plus 4. And while I'm at it, remember this just gets copied down. So while we're at it, let's take its derivative, and we'll see. This is a good way to test. So take the derivative of 3x plus 4. Derivative of 4 is 0. Derivative of 3x is just 3 dx. What a beautiful little integration there. This is going to be nice and easy for us, hopefully. But notice it's gone. There's no variable anymore. Okay, so then what do we have to do for this other side, this other part, all of this here, e to the minus 5x dx. Now, as beautiful and as simple as that looks down there, this might look a little challenging, but we'll be okay. There's one of those memory ones that says basically when you're integrating this, you'll get e to the minus 5x divided by this constant here, divided by minus 5x. And if you aren't sure, let me kind of do that over here. So we let u equal minus 5x, then du is minus 5 dx. Divide both sides by minus 5, you get minus 1/5 du equals dx. Remember all of this. So u substitution, so we're going to integrate e to the u because we made minus 5x equal u, and then the dx becomes negative 1/5 du. And remember, this is where we split the pieces. I shouldn't call them pieces because we're dealing with pieces now, but we split them, and then this just integrates as e to the u times negative 1/5, or if you want, over that, and then you back substitute. So you get e to the minus 5x over minus 5, and you get a minus out here because basically the minus 5 will come down because of the chain rule. We need this here so that when we do take its derivative and it comes out, that will cancel out. Okay, so not two negatives, I got just one negative, okay, just one down here. In fact, let me erase that. Doing math, I usually don't like the eraser because you want to keep your mistakes there so that you can understand what you're doing. Okay. Anyway, this is what v is now. V is e to the minus 5x, and again you have 1 over 1/5 if you want. Oh, let's do that. I think that's better. Copy it down here. That's what it is. Now let's put our pieces together. So this, and again I'll put a parenthesis around it, we're going to get 3x plus 4 times negative 1/5 e to the minus 5x, and we'll move that to the front, and you could distribute it through. There's a lot of things you could do, but that's our front part. The back part is this is our v, this is our du. So I'm just going to write it out, and then we'll clean it up later. E to the minus 5x. So that's that first part times 3 dx. Okay. So this part, remember, this is, and actually I guess I should put like a parenthesis here. So I'm going to move the negative 1/5 to the front. I'm going to keep this in its little bubble. And then we've got e to the minus 5x. So that's a nice looking little thing in the front. Then we've got this minus, but we've got a minus here too. And I can see I've got a 1/5 and a 3. That's a constant multiplier. I'm actually going to bring those out. So I'm going to change that minus to a plus, and I'm going to bring 3/5 to the very front because that's just a constant number, a multiplier. We bring it out, it cleans up the inside a little, actually a lot, right? E to the minus 5x dx. And so we've got one step left. The front part is all good, all very copacetic. Copacetic means, I don't know, like good shape or something. It's just kind of one of those words you learn to say it and it just sounds cool, but you don't really ever know what it means. Okay, and so now we're going to get 3/5, right? 3/5 just comes along, but remember when we integrate this, we've already done this up here. We're going to get a minus 5 coming off, right, in the denominator. So because this is going to be, remember, e to the minus 5x over minus 5, and then we're going to multiply that times 3/5. So I'm just trying to save myself from writing too much, but I guess I wrote it over here, right? We're going to get a minus 25 in the bottom, and in the top we get 3e to the minus 5x over 25, but here's one of those things, it's got a minus here, don't forget about it. So we're going to change that plus back. And again, let's, come on, give me my eraser. There it is. We're going to change that back to a minus now to take care of that. So be careful, watch over those negatives, and again, since it's an indefinite integral, we always get some kind of plus a c out here. So I remember doing these when I learned them. No one ever showed me this method. We did break it down into u, v, but and I'll tell you, this wasn't my idea. It sort of was. I adapted it, but it was in the PowerPoint. I went through the PowerPoint. They showed this. I said, oh, that's kind of cool. Let me see if I can adapt it a little bit. And so I've made it a little different. So the PowerPoint's there. If you want to look through it, it gives some explanations. It does show sort of this in a little different form. To me, this just follows for me, and I hope it works for you. I think it will. But the other one's in there if it works better for you. Okay, so here's another e to the x. So see if we get all this stuff out of the way. Let's see. Forget to check to see if my head was blocking anything. Okay, we're all okay. And we're just going to keep slowly going through this. You want to take a break, take a break. You want to fast forward me, fast forward me. But I kind of like teaching this way. We got all the time we need, as long as you understand you can fast forward or back it up and whatever we need to do. So we'll follow through with this. We know that e to the x will never differentiate out. It's always going to be there. So we don't want to make it u. What we want to make the u part is the part that will disappear on us. So 2x. And again, the first step, I love it. Copy it. I can do that. Second step is to take its derivative, 2x. The derivative of 2x is going to be 2 dx. And remember that dx kind of comes off because we're taking the derivative with respect to x. So that's that part. The dv part, we're going to switch colors here. The dv part is all of this, e to the x dx, e to the x dx. Remember, to get down to here, we go from dv to v. Well, how do you get there? You integrate. So integrating e to the x, we get e to the x. That's why I like e to the x. It's like it knows who it is. Whether it's an integral or differential or just being itself, it's always itself. It's kind of cool. Okay, copy it down. Now put the pieces together. Okay, so over here we get 2x e to the x, u times v, that's it. That's those pieces. Over here, this is v du, v du. So we get e to the x 2 dx. And again, we'll bring that 2 to the front, but we'll wait to clean things up. We'll just leave it all like that. Okay, so we get 2x e to the x minus, bring the 2 out front, integral e to the x dx. Again, we're not quite done. We've still got an integral, so but it's a simple integral. We don't need to do integration by parts. The parts part took care of this. Again, on the last one, I didn't take its derivative to prove that it was, but you could. I'll let you do that as an exercise. You should be able to practice that steps. So where are we? We need to take this integral. So again, the front part is done. And when we integrate this, we get 2 e to the x integrated is just e to the x. Doesn't look like anything happened, but it did. That's it, plus a constant. And you're seeing we're kind of, the reasons we need to do integration by parts is basically whenever we have an e to the x or a natural log of x, we have just polynomials. Usually we can handle that with the other methods we've got. Okay, so this one looks daunting. It's got a fraction, shoot. But remember, we can get this, just move it up. So the first step we're going to do here, I'll stay with blue. We're going to rewrite this. 2x plus 1 parentheses e to the minus 8x. This is just like one we did, right? Except it had a minus 5 here, something else there. But now it looks okay. Now it's doable. There's the u part. And so we write it down, right? Just copy, take its derivative. Derivative of 1 is 0, derivative of 2x is 2 dx. Yeah, we're picking up some speed here even. Okay, this part is the dv part, e to the minus 8x dx. So to get down to make this into v, what we have to do is, I guess what we're really doing is, taking the derivative, taking the integral of both sides. So integral of dv becomes v. Integral of this, remember, will become e to the minus 8x over minus 8. Because that's, when you take its derivative, the minus 8 comes down. We need it to cancel to get back to where we started, if that makes any sense, sort of. Okay, so that's our v. And basically, I just didn't go through all the u substitution part we did on the other one. We could, but okay. So now we put the pieces together. We could, but we're not. I'm not. Okay. 2x plus 1. Although you may ask me to later. We'll do it. We'll do it as many times as you want. I'm going to rewrite this. Didn't I write that like 1/8? I think I'll put that there. E to the minus 8x. We'll do like that. Do the same thing here. Minus 1/8 e to the minus 8x 2 dx. I didn't give myself a lot of room, but I think we're going to be okay. There's a question under here. So we get 2x plus 1. Just like last time, I'm going to move the minus 1/8 to the front. Let me check something. Did I make it a minus 1/5? I did. Good. I caught my minus 1/5. Sometimes I forget those negatives. Just had to check. Okay. E to the minus 8x. So that's the front one, right? I just reorganize this, guys. We've got a minus and a minus. That's going to come down, but remember, we'll probably get a minus back. So, well, let's just keep track of what we're doing at one at a time. Negative times negative is a positive. We'll trade it back when it needs to get traded. 1/8 comes in front. Actually, no, 2 over 8, so 2/8 is 1/4. Right? We can reduce it down to 1/4. So 1/8, 2 on top, reduces down to 1/4. E to the minus 8x dx. We now can integrate this part. So our final answer is all this front part. I know, it's just, you have to keep, that's one of the things with math, you just have to keep copying over things. Or if you're smart enough, there's probably a way to copy and paste it. Now notice when we integrate this negative, it's going to divide by -8, so that's going to become a minus. We're going to have a, remember this -8 is going to be the bottom, so 8 times 4 is 32. So that, what happened, the 8 came down, 8 times 4, the plus became a minus, so we took care of that, and then it's just e to the minus 8x plus a constant. Okay, that's what we got. We are in very good shape. Okay. I think we got one more. Maybe we got two more. Let's see, we got this one. I thought we had one more after that. Is that the last one? And then what I've got down here is just some blanks, so you can fill in your own. If you wanted to print this out and just use it as sort of a scaffolding, or if you've got an iPad with a pencil or some kind of writing device, you can just kind of use these as templates for whatever you want. Now, this one looks like the hardest one of the day, but you know what? We're going to be okay. So, okay, we go for this one. So we got a rocket rising from the ground. It's got a velocity. Remember, velocity is the derivative of position. Okay, this is the derivative of position. So they give us this. How far does it rise in the first 3 minutes? That's a position question. And so what they're really asking us to do is to integrate this and go from 0 to 3 the first 3 minutes. But one of the things you're going to need to worry about or be careful about here is units. This is in seconds and this is in minutes. So since our function's in seconds, we want our x values, our t values, whatever, our time values to be in seconds. So we take 3 minutes, and what there is in 1 minute there are 60 seconds. So the minutes cancel. 3 times 60 is 180 seconds. So we're going to go, what we really want to do is we want to go for the interval from 0 to 180. That's what they're asking, 180 being 3 minutes. So this is what they're asking us to do. Integrate from 0 to 180 this function, 1500 t e to the minus t over 180 dt. Again, you could change them to x's. The thing is since it is a definite integral going from here to here, we could do it with the integration by parts. And if we were going to, I'll just leave it in color because I'm not going to use it actually. I'm going to show you we can do it with the calculator. I would put this part as my u. I would put e to the minus t over 180 dt. This is the part I would integrate. This is the part I would differentiate. This one's not too bad. You get 1500 dt, right? So that'll just go there. This one's not too bad. You get, and actually since the 180 is in the denominator, it's going to flip, and so you're going to get minus 180 e to the minus t over 180. Okay, so that's v. I said we weren't going to do it, and here I am doing it, right? I'm just letting you know there's also an easier way to do this. So But I do want you getting practice with this, so then we put our pieces together over here. That's the part I'll let you do. What I'm going to show you is, where's my calculator here? Here it is. Let's get this thing fired up. I'm still on my free trial. I had a 90-day free trial, so I got 8 days left. I'm probably going to have to buy. I will buy one eventually. I had one before. That's the thing. I've had actually several of these, um, but on like my work computer, so I had to leave that behind. When I left the community college, I had it on a laptop, and that thing fell off the back of my motorcycle on the freeway and got kind of crunched. But anyway, I'm a good citizen. I'll follow through and I'll buy this once the free period's over. Let's see, let's come back. Let's bring this guy back up. Okay, so this is in front. So what we're going to do is we're going to um, remember actually graphing the derivative function, and we use x instead of t. E. Now here's the tricky part. You want to make sure all of this is up. Now some of you are going to need to put a parentheses to make sure all of this is in the exponent. I'll just put it. I don't really need it with this system, but I'll put it there. Okay, so there's that. What I go to is I'm going to graph it. And remember, we're going from 0 to 180. Those are x values, so I want to make sure my x window's large enough, and I did run this. So I went from -1 to 200. You could go from 0 to 200. I like to have just a little bit of space around here, so a little bit more than 180. I did have to play with how big the window, and I found that 3000 was a good setting for this, but it took me a while. I started with 10,000, and you didn't see much, and then I tried them like a million. You saw too much. But notice now this is a good graph, but it took me about 5 iterations to get to this kind of a graph where it looked good. I could actually make it smaller. Let's do this. Let's go 200,000. And you'll see we see a little bit more. I guess, could have probably 100,000 would have worked. But anyway, we're going to go from, so what we do is we go second calc. Number 7, the lower limit is 0, and the upper limit is 180. Okay. Now some of you might have tried 0 to 3 because it says 3 minutes, but you wouldn't get, that would really be going from 0 to 3 seconds. We've got to get our units to match up. They did this on they put that Hubble Space Telescope, and they didn't convert from centimeters to inches or something. Multi-million-dollar mistake, just not being the right units. We got to do that. We got to check our units. So our answer, here it is 1,128.42,118, and it does say round to the nearest foot, and so it's done. It's to the nearest foot, and we put, so that's 12 million feet. That's quite a rocket. 12 million feet. That's a lot. Anyway, that's the right answer. Plug it in. There's one in there in the WebAssign that's similar to this, a little different, but you can approach it the same way. So you don't have to go through the integration by parts because it's a definite integral, and we can use the technology on definite integrals. And that's what a good business student is about, right? Finding the most efficient way to get to the answer so that you can get the data you need to make decisions. That's what this is for. And so hopefully that's going to help you out. Let's see. That's pretty much it. There's some extra ones for you to practice. I also, basically in the homework, each problem will be similar to one of these. Again, the details are a little bit different, but they follow pretty much. They're either an e to the x with something times in the front. Sometimes it's a little bit more of, or it's a natural log with something in front. Follow these patterns, and you'll be just right on track. So integration by parts. There's our formula that we're using, and that's really all you need to know about it. Take a look at the PowerPoint if you'd like more explanation. Um, and if you'd like to see the source of where I got this idea, which I just slightly adapted, I think, maybe, but yeah, that's basically what they did. They had these four boxes, put your stuff here and move over. I added the little arrow guys. I thought that was cool. So that's my contribution. So good luck. Get your homework done on 14.1 and use this method if you'd like, or some other method if it's more meaningful to you. Um, but then we're putting us right together, and the next few units we're going to take a look at will all be about applying the integration techniques we've already learned. Thanks.